What if everything you thought about time, your past, your future, your very existence, could be rewritten? Imagine for a moment that time isn't the unshakable force we perceive it to be, but rather a complex and malleable dimension waiting to be unraveled. Time travel, once confined to the realm of science fiction, has captivated our imaginations for centuries. From ancient myths to blockbuster films, it's a concept that bridges the boundaries of science, philosophy, and culture. But what if the key to traversing time isn't just a dream? What if it's grounded in theories that scientists and thinkers have spent decades exploring? In this video, we're diving headfirst into the mysteries of time travel, uncovering 25 fascinating, mind-bending theories that just might explain how moving through time could work. Whether it's bending space-time, tapping into quantum mechanics, or even flirting with parallel universes, each idea challenges what we know about reality. So, buckle up as we journey through the possibilities, because by the end, your perception of time may never be the same. Moving forward, we begin with one of the most groundbreaking ideas in modern physics, Einstein's theory of general relativity. This theory transformed our understanding of the universe by revealing that space and time are not separate but interconnected, forming what scientists call spacetime. Picture spacetime as a flexible grid that can bend, stretch, or warp under the influence of massive objects. According to Einstein, this warping isn't just a quirk of physics, it's the very mechanism that gives rise to gravity. Now here's where things get fascinating. If spacetime can bend and curve, it could, in theory, fold in on itself, creating shortcuts often referred to as wormholes. Imagine two distant points in the universe connected by a tunnel, allowing for instantaneous travel between them. This concept has sparked countless imaginations, from physicists to science fiction writers. But the possibilities don't end there. Extreme gravitational fields, such as those near black holes or other massive celestial bodies, could potentially distort time itself. Under the right conditions, these distortions might make it possible to move forward or backward along the timeline. While these ideas remain largely theoretical and face significant scientific and technological challenges, Einstein's work gave us the first glimpse of how time travel might not just be a dream but a mathematical possibility rooted in the fabric of our universe. As we unravel these concepts, the next chapter of our journey takes us deeper into the mystery of wormholes and their role in bending time and space. Now turning to the intriguing concept of wormholes, these hypothetical structures have fascinated scientists and storytellers alike for decades. A wormhole, also called an Einstein-Rosen bridge, can be imagined as a tunnel that connects two distant points in spacetime. Picture folding a piece of paper so that two spots on its surface touch, then poking a hole through both layers. This is essentially how a wormhole is theorized to work. If such a phenomenon could exist, it might allow for instantaneous travel between two locations, no matter how far apart they are in the universe. But wormholes do not only offer shortcuts through space, they also hold the tantalizing potential for time travel. By connecting two different points in time rather than just space, a wormhole could theoretically allow someone to step into one end and emerge in the past or future. However, this idea is riddled with challenges. For starters, wormholes are thought to be incredibly unstable. The moment anything tries to pass through, they would likely collapse under their own weight. Additionally, the energy needed to stabilize a wormhole is nothing short of astronomical, requiring a form of theoretical matter with negative energy, something physicists call exotic matter. Exotic matter, while possible in theory, has not been observed or understood in practical terms. Furthermore, even if we could stabilize a wormhole, navigating one safely would be an entirely different problem due to the immense gravitational forces at play. As captivating as this theory is, it remains purely speculative at this point, a mathematical possibility without experimental confirmation. Still, wormholes continue to inspire both scientific inquiry and the creative minds behind science fiction, keeping the dream of bending time and space alive. As we navigate these captivating ideas, the next step in our journey introduces us to another extraordinary concept: Tipler cylinders and their potential for enabling time travel. Moving forward, we delve into the fascinating concept of Tipler cylinders, named after physicist Frank J. Tipler. This theoretical idea proposes a unique method of time travel by utilizing a rapidly spinning, infinitely long cylinder. According to Tipler's calculations, if such a cylinder were massive enough and spun at an extraordinary speed, it could twist the very fabric of spacetime around it. This twisting effect might create what physicists call closed timelike curves, essentially loops in spacetime that could enable travel back and forth in time. Imagine spiraling along this loop and arriving at a different moment in the timeline. However, as promising as this sounds, the concept of Tipler cylinders is not without its challenges. For one, the requirement for the cylinder to be infinitely long and possess an almost unimaginable amount of mass makes it practically impossible to construct with any materials known to humanity. Additionally, the energy required to maintain such rapid rotation would be extraordinary, far beyond our current technological capabilities. Even more perplexing is the question of stability. The immense gravitational forces generated by this spinning mass could potentially disrupt the very spacetime it seeks to manipulate, leading to unpredictable and hazardous outcomes. While Tipler cylinders remain an exciting mathematical possibility, they highlight the immense obstacles that lie between theoretical physics and practical time travel. Yet, the exploration of such ideas continues to inspire and expand our understanding of the universe. As we unravel these theoretical possibilities, the next chapter invites us to explore an equally enigmatic concept: the role of cosmic strings in the quest for time travel. Now turning to the intriguing idea of cosmic strings, we encounter a concept that stems from the very origins of the universe itself. Cosmic strings are theoretical structures believed to be remnants from the Big Bang, formed as the universe rapidly expanded and cooled. Picture them as unimaginably thin, yet incredibly dense filaments stretching across vast distances in space. To put their density into perspective, a single cosmic string, though thinner than an atom, could weigh as much as an entire planet. Their immense gravitational pull creates a profound effect on spacetime, bending and warping it in ways that open up fascinating possibilities for time travel. According to physicists, if two cosmic strings were to pass by each other at high speed, or if a cosmic string were to loop around itself, the result could be a closed timelike curve. This means that spacetime would bend so drastically that it could, theoretically, form a loop where one might travel back in time. However, the challenges of utilizing cosmic strings for time travel are as immense as the strings themselves. For one, these structures remain hypothetical, with no direct evidence of their existence despite rigorous scientific exploration. Even if they do exist, the energy required to interact with or manipulate them would be orders of magnitude beyond what humanity can achieve today. Moreover, the stability of such a configuration is highly uncertain, with the potential for catastrophic consequences if things were to go awry. Nevertheless, cosmic strings offer a tantalizing glimpse into how the universe's earliest moments might hold the key to unlocking the mysteries of time travel. Moving forward, we dive into yet another captivating theoretical framework: the concept of closed timelike curves, where time itself might flow in loops in the fabric of spacetime. Moving forward, let's delve into the fascinating concept of closed timelike curves, a theoretical construct that emerges from solutions to Einstein's field equations in the realm of general relativity. Closed timelike curves describe loops in spacetime where time itself could, in theory, cycle back on itself. Imagine tracing a path through spacetime that eventually leads you back to the very moment and place where you started, a journey not through physical space but through time. These curves open the door to the possibility of traveling backward in time, creating a tantalizing avenue for exploring the mechanics of time travel. Yet the concept of closed time-like curves is not without its challenges and controversies. One significant hurdle is the potential for paradoxes. For instance, there is the famous grandfather paradox, where a time traveler could theoretically alter the past in a way that prevents their own existence, raising the question of whether such loops in space-time could ever coexist with the consistency of cause and effect. Some physicists argue that the existence of closed time-like curves might imply alternate timelines or even self-consistent histories, where any actions taken by a time traveler would naturally fit into the fabric of space-time without causing contradictions. Philosophically, this theory forces us to confront deep questions about the nature of reality, free will, and determinism. If closed time-like curves are indeed possible, do they imply that the future is already set in stone, or do they allow for the flexibility of multiple outcomes? While purely theoretical at this stage, closed time-like curves continue to spark intense debate and exploration, offering profound insights into the structure of the universe and the possibilities of time. As we unravel these intriguing ideas, our next step leads us into the quantum realm, where the mysterious phenomenon of quantum entanglement might hold clues to unlocking the secrets of time travel. With the next phase of the journey in sight, we now shift to the captivating quantum realm to explore quantum entanglement, a phenomenon that continues to baffle and intrigue scientists. At its core, quantum entanglement describes a mysterious connection between particles, where the state of one particle is instantly reflected in another, no matter how far apart they are, whether separated by mere inches or light years across the universe. This spooky action at a distance, as Albert Einstein famously described it, seems to defy our traditional understanding of space and time. Could such an enigmatic link between particles offer a gateway to time travel? Some theorists propose that entanglement might hold the key to transmitting information or even influencing events across time. Imagine, for instance, a pair of entangled particles so deeply connected that manipulating one could potentially ripple across time to affect the other. While this idea is firmly rooted in speculation, it opens up tantalizing possibilities for how the fabric of spacetime could be intertwined with quantum states. However, the road to understanding this phenomenon is far from clear, as quantum entanglement challenges many of our preconceived notions about causality and the flow of time. Experiments have repeatedly confirmed the reality of entanglement, but how this phenomenon might interact with or impact time itself remains an unanswered and profoundly complex question. As we grapple with these mysteries, it becomes evident that quantum entanglement serves as a reminder of just how little we truly know about the universe. Moving forward, let us shift to a concept that has already been observed and proven, time dilation, and uncover how it demonstrates time travel into the future, not just as a theory but as a reality grounded in Einstein's work. With the next phase of the journey in sight, we delve into time dilation, a fascinating phenomenon that isn't just theoretical but has been tested and proven by Einstein's groundbreaking work. Time dilation occurs when time moves at different rates depending on relative speed or gravitational force. Simply put, time slows down for an object moving at extremely high speeds or near a strong gravitational field compared to an object at rest. A striking example of this comes from the experience of astronauts. Imagine an astronaut traveling on a spacecraft moving close to the speed of light. For them, only a few years might pass on board, but when they return to Earth, decades or even centuries could have gone by for everyone else. This effect has been experimentally confirmed with precise atomic clocks placed on fast-moving jets or satellites. These clocks were found to tick slightly slower than identical clocks on the ground, proving that time dilation is very real. Another vivid demonstration lies in the intense gravitational pull of massive objects like black holes. If you were to approach a black hole's immense gravity, time for you would slow to a crawl compared to someone far away from it. This means time dilation not only allows us to glimpse the possibility of time travel, but shows how journeys into the future are indeed achievable, at least in theory. It underscores how Einstein's insight shifted our understanding of time from a fixed, universal constant to a flexible dimension that can be stretched or compressed depending on circumstances. With such profound implications for our perception of reality, time dilation continues to be one of the most captivating aspects of modern physics. Moving forward, let's explore the intriguing idea of tachyons, hypothetical particles so quick they may hold the key to unlocking time travel possibilities. Now turning to the fascinating concept of tachyons, we encounter a theoretical particle that has captured the imagination of many physicists and science enthusiasts alike. Tachyons are proposed to travel faster than the speed of light, a feat that violates our conventional understanding of physics. According to Einstein's theory of relativity, nothing in the universe can exceed the speed of light. However, tachyons, if they exist, would break this rule and open up extraordinary possibilities, including time travel. The idea is that because tachyons always move faster than light, they could theoretically send information or even objects back in time. Imagine receiving a message today that was sent from the future. This tantalizing scenario hinges on the existence of these elusive particles, but tachyons remain purely speculative, as no experimental evidence has yet confirmed their presence. Their hypothetical nature stems from equations in physics that suggest faster-than-light particles would have imaginary mass, a concept that is hard to reconcile with our current understanding of the universe. Despite their speculative status, tachyons serve as a thought-provoking example of how science pushes the boundaries of what we consider possible, challenging us to rethink the very fabric of space and time. With the mysteries of tachyons lingering in our minds, let us now journey into the multiverse theory, an idea that takes time travel into an entirely new dimension. With the next phase of the journey in sight, we step into the extraordinary concept of the multiverse theory, a mind-expanding idea that suggests our universe may not be the only one. Instead, there could be countless parallel universes existing simultaneously, each with its own unique timeline. Imagine a reality where every choice you could ever make results in the creation of a new universe, a branching network of infinite possibilities. According to this theory, time travel might not involve revisiting the past or future within our own universe, but instead traversing these alternate realities. For example, entering a parallel universe where events unfolded differently could feel like stepping into a different timeline altogether. Scientists speculate that if multiverses exist, they might be connected in ways we do not yet understand, potentially allowing for movement between them. This could mean that a journey to another universe might provide access to a period that mirrors the past or future of our own, offering a fascinating twist on the concept of time travel. However, much like the tachyons we just explored, the multiverse theory remains largely theoretical, as we currently lack the tools to observe or prove the existence of parallel universes. Nevertheless, it continues to inspire both scientific inquiry and popular imagination, pushing us to reconsider the possibilities of time and existence. Moving forward, let us now venture into the mysterious depths of black holes and their potential role in time travel. Now turning to the enigmatic phenomenon of black holes, we delve into their potential role as gateways for time travel. Black holes are regions in space where gravity is so overwhelmingly strong that nothing, not even light, can escape their pull. According to Einstein's theory of general relativity, their immense gravitational force bends spacetime itself, creating a warp so extreme that time could behave in unexpected ways near their event horizons, the boundary beyond which nothing can return. Some scientists theorize that if one could approach a black hole without being destroyed, it might be possible to exploit these distortions in spacetime to travel to the future or even the past. For example, time near the event horizon moves significantly slower relative to an outside observer. This means that someone orbiting close to a black hole might experience only hours passing, while years or even centuries pass for those farther away. However, the journey to a black hole, let alone surviving its vicinity, is riddled with challenges. The intense gravitational pull creates a process humorously nicknamed spaghettification, where an object or a person would be stretched into a thin strand due to extreme differences in gravitational forces between their head and feet. Furthermore, even if one could safely navigate these dangers, the questions remain. Where would they end up, and would it even be possible to return? Although black holes ignite our imaginations, their mysteries remain largely unsolved, with current technology unable to explore their depths. They stand as cosmic enigmas, tantalizing humanity with the possibility of time travel while reminding us of the vast unknowns of the universe. As we move ahead, let us explore something equally fascinating yet quite the opposite: white holes, the theoretical counterparts to black holes, and their speculative connection to time travel. As the next phase of our exploration begins, we turn our attention to an equally intriguing concept: white holes, the theoretical counterparts to black holes. Unlike black holes, which trap everything within their grasp, white holes are hypothesized to do the opposite, allowing matter and light to escape but never permitting anything to enter. While no white hole has been observed, the idea stems from mathematical solutions to Einstein's field equations, suggesting their existence as a possibility. Some physicists speculate that white holes could be linked to time travel by serving as exit points connected to black holes through a hypothetical tunnel known as a wormhole. Imagine entering a black hole and emerging through a white hole, potentially arriving at a different point in time or space. This idea remains purely theoretical, as the extreme conditions near such phenomena would likely make them impossible to traverse. Furthermore, white holes present their own paradoxes, such as how they could form and remain stable in a universe dominated by entropy. Despite their mysterious and speculative nature, white holes offer a glimpse into how much we have yet to understand about the fabric of spacetime. As we move forward, let us navigate deeper into the realm of quantum mechanics and explore the many worlds interpretation, a theory that offers a fascinating twist on the nature of time travel itself. Now turning to the fascinating world of quantum mechanics, we arrive at the many worlds interpretation, a theory that fundamentally redefines our understanding of reality and time travel. According to this interpretation, every decision or event creates a branching universe, resulting in countless parallel realities existing simultaneously. Picture it like an infinite tree where each branch represents a different timeline stemming from a unique choice or occurrence. For instance, in one universe, you may have chosen to take an entirely different path in life, while in another, you might be living an alternate version of today's events. The many worlds interpretation suggests that time travel might involve traversing these branches, allowing someone to step into a parallel universe where the timeline unfolds differently. This concept bypasses many of the traditional paradoxes associated with time travel. Instead of altering one fixed timeline and potentially causing logical inconsistencies, such as erasing your own existence, you would simply shift into a different reality where alternate possibilities play out. However, this fascinating idea raises its own questions. If these alternate universes truly exist, how could we ever interact with or navigate between them? Current science hasn't provided a concrete mechanism for accessing these parallel worlds, but the theory remains a captivating way to think about time travel and the boundless possibilities of existence. The many worlds interpretation invites us to imagine a reality that is far more complex and interconnected than we ever thought possible. With our understanding of quantum mechanics expanding, this theory serves as a reminder of how much we have yet to uncover. Moving forward, let us delve into the intriguing Novikov self-consistency principle, a theory that proposes solutions to the paradoxes of time travel while maintaining consistency within a single timeline. Moving forward, we encounter the Novikov self-consistency principle, a concept designed to tackle the puzzling paradoxes of time travel, particularly those like the infamous grandfather paradox. Imagine traveling back in time with the intention of preventing your own grandfather from meeting your grandmother, an act that would theoretically erase your own existence. According to this principle, such a scenario is impossible. The Novikov self-consistency principle asserts that the laws of physics would always work to preserve consistency within a single timeline. In other words, any action taken by a time traveler in the past must already align with the events that have occurred in that timeline, ensuring that no contradictions arise. For example, even if you attempt to alter a significant historical event, your actions would somehow become part of the chain of events that lead to the very future you come from. This principle suggests that while time travel might be possible, it comes with strict limitations on what can and cannot be changed. It effectively eliminates the potential for creating alternate outcomes or branching realities within the same timeline, maintaining a coherent and self-consistent history. However, while the Novikov self-consistency principle provides a theoretical solution to time travel paradoxes, it also raises profound questions about free will and destiny. If your actions in the past are already predetermined to align with the timeline's consistency, does that mean your choices are ultimately an illusion? Despite these philosophical implications, the principle remains a cornerstone in discussions about the mechanics of time travel. As we continue to ponder these thought-provoking ideas, let us now delve into the intriguing notion of retrocausality, a concept where the future could influence the past, further expanding our understanding of time's enigmatic nature. Now turning to the fascinating concept of retrocausality, we explore a theory that challenges our traditional understanding of cause and effect. Retrocausality suggests that the future might influence the past, creating scenarios where an effect occurs before its cause. Imagine, for instance, receiving a mysterious message today that somehow prompts you to take an action tomorrow, which in turn leads to the very circumstances that resulted in the message being sent in the first place. This mind-bending idea flips our conventional perception of time on its head, opening the door to profound possibilities. In the context of time travel, retrocausality implies that actions or decisions made in the future could ripple backward, shaping past events in ways we might not fully comprehend. Some interpretations of quantum mechanics, particularly those dealing with entangled particles, lend a hint of plausibility to this concept, as they demonstrate peculiar connections that seem to transcend the limits of time and space. However, retrocausality is not without its challenges. It raises intriguing questions about the nature of reality, free will, and determinism. If the future can influence the past, does this mean the timeline is fixed with every event, both past and future, predetermined? Or does it imply a more flexible relationship where reality adapts dynamically to maintain coherence? While retrocausality remains speculative and deeply theoretical, it serves as a compelling lens through which we can examine time travel's enigmatic possibilities. It pushes us to think beyond the linear progression of time we experience in everyday life, encouraging us to embrace the notion that time might be far more complex than we have ever imagined. With these provocative questions in mind, let us now move deeper into the realm of time loops, exploring how certain conditions could cause events or individuals to repeat endlessly, further unraveling the mysteries of temporal phenomena. Now turning to the concept of time loops, we delve into a phenomenon that has captured the imagination of countless storytellers and scientists alike. A time loop refers to a scenario where events or individuals become trapped in a cycle, endlessly repeating the same sequence of occurrences. This idea has been vividly explored in science fiction, with examples like the movie Groundhog Day, where the protagonist relives the same day repeatedly, or Edge of Tomorrow, which depicts a soldier caught in a loop of combat and death. These stories often highlight personal growth or problem solving amid the seemingly eternal repetition, but the theoretical foundation behind time loops extends beyond fiction. In physics, time loops are tied to the concept of closed timelike curves, which are solutions to Einstein's equations of general relativity. These curves suggest that spacetime could bend back on itself under specific conditions, creating a loop where an object or even a person might relive the same moments endlessly. Such a scenario requires extreme circumstances, like the presence of immense gravitational forces or unique spacetime distortions caused by phenomena such as wormholes or cosmic strings. While these conditions remain hypothetical, they demonstrate how time loops might exist within the framework of modern physics. However, time loops also pose intriguing questions. If an individual were trapped in such a cycle, could they ever break free, or would their actions always lead back to the same starting point? Furthermore, how does memory function in a loop? Would the person retain knowledge of prior cycles? And if so, what implications would this have for free will and determinism? Time loops challenge our understanding of progression, transformation, and choice, illustrating yet again that time might operate in ways far stranger than we perceive. Moving forward, let us explore the fascinating discovery of time crystals and how they might offer new insights into the mysteries of time and its potential manipulation. Moving forward, we dive into the intriguing world of time crystals, a groundbreaking discovery that introduces a previously unknown phase of matter. Unlike traditional crystals, which exhibit repeating patterns in space, time crystals display patterns that repeat in time. This means they move and evolve with a kind of perpetual motion, even when in their lowest energy state, defying conventional expectations of how matter behaves. First theorized by physicist Frank Wilczek in the year 2012, and later realized experimentally in the year 2016, time crystals do not violate the laws of thermodynamics, but instead reveal a remarkable symmetry in time itself. Their unique ability to oscillate indefinitely without consuming energy has captured the interest of scientists exploring the fundamental nature of time. The implications for time travel stem from their relationship to quantum mechanics and the potential to manipulate time-related phenomena. If time crystals can maintain stability across temporal dimensions, they might offer clues about creating or navigating time loops or enabling new methods of temporal control. Imagine the possibility of using these endlessly oscillating structures to anchor or traverse across different moments. Although this is still in the realm of theoretical science, the existence of time crystals pushes the boundaries of what we know about time, quantum mechanics, and the potential for manipulating them. Moving forward, we turn our attention to the concept of the Alcubierre warp drive, a speculative idea that could revolutionize travel across both space and time. Now turning to the concept of the Alcubierre warp drive, we encounter a theoretical breakthrough proposed by Mexican physicist Miguel Alcubierre in the year 1994. This idea suggests a method of faster-than-light travel by bending spacetime itself, a feat that could fundamentally alter how we perceive movement through both space and time. The mechanism of the Alcubierre warp drive involves creating a warp bubble, where space-time is compressed in front of a spacecraft and expanded behind it. This would allow the ship to move faster than light relative to external observers, without violating the universal speed limit set by Einstein's theory of relativity, because the spacecraft itself would remain stationary within the bubble. The most tantalizing aspect of this concept is its potential link to time travel. By warping spacetime in such a way, the boundaries between past, present, and future could theoretically blur, opening possibilities for traversing through different moments in time. However, this idea also faces significant challenges. For one, it requires a form of exotic matter with negative energy density to stabilize the warp bubble, a substance that has not yet been discovered or proven to exist. Furthermore, the energy requirements for such a drive, based on initial calculations, would be astronomical, potentially surpassing the energy output of an entire star. Despite these challenges, the Alcubierre warp drive remains a fascinating glimpse into what could one day be achievable if our understanding of physics evolves. As researchers continue to investigate the wild frontiers of spacetime manipulation, the dream of bending the universe to our will persists. Moving forward, we delve into the philosophical and well-debated grandfather paradox, a thought experiment that questions the very fabric of time travel itself. Now turning to the famous grandfather paradox, we encounter one of the most perplexing challenges to the concept of time travel. Imagine this: you travel back in time and inadvertently prevent your grandfather from meeting your grandmother. If that event occurs, it means one of your parents would never be born, and consequently, you would not exist to travel back in time in the first place. This creates a logical contradiction, a loop that seems impossible to resolve. The grandfather paradox forces us to confront the fundamental question of whether actions in the past can truly be altered without unraveling the very fabric of reality. Philosophers and physicists have debated this conundrum for decades, offering intriguing solutions. One such theory is the multiverse hypothesis, which suggests that any change made in the past could create an entirely new parallel universe. In this scenario, your actions would not erase your existence in your original timeline, but instead branch off into a separate reality where the course of events unfolds differently. Another proposal is the Novikov self-consistency principle, which argues that the laws of physics would prevent any action that causes a paradox. According to this principle, events in the timeline are fixed, meaning that if you were to travel back in time, you would only be able to fulfill events that have already occurred, not alter them. This would ensure consistency and eliminate contradictions. Both theories offer elegant yet wildly different ways to think about the paradox, each challenging our conventional understanding of cause and effect. As we grapple with these mind-bending ideas, it becomes clear that time travel is not just a scientific challenge, but also a deeply philosophical one. With that in mind, let us move forward to explore the block universe theory, a perspective that redefines how we perceive the past, present, and future within a single, unchanging structure. Moving forward, we arrive at the block universe theory, a perspective that challenges our very perception of time itself. According to this idea, the past, present, and future are not separate, fleeting moments, but rather coexist simultaneously within a single, unchanging structure. Picture time as a four-dimensional block where every moment from the dawn of the universe to the distant future exists together in a vast, interconnected tapestry. In this framework, time is not something we flow through but a dimension similar to space that we inhabit. This reimagining of time creates a fascinating possibility for time travel. If all moments are already laid out within the block, then theoretically, traveling to any specific point in time becomes a matter of navigating the structure. However, this concept raises profound questions. If every event is already part of the block, does that mean free will is an illusion? Are our actions predetermined, or do we still have agency? Supporters of the block universe theory argue that this model avoids paradoxes altogether, as any time travel would simply involve moving within a fixed structure where events remain consistent. For instance, if you were to travel back in time, you would not change the past. Rather, your actions would already be embedded in the fabric of the block, contributing to the sequence of events as they are meant to unfold. This idea provides a deterministic view of the universe, suggesting that everything, including time travel, fits neatly within the grand design of space-time. While the block universe theory offers an elegant framework for understanding time, it also challenges our most intuitive beliefs about existence and free will, leaving us to wonder, is time a river flowing endlessly forward, or a frozen canvas we are merely observing? With these deep questions in mind, let us delve into the intriguing world of quantum mechanics, where the concept of quantum foam might hold the key to manipulating spacetime itself. Now turning to the mysterious realm of quantum mechanics, we explore the concept of quantum foam, a term that describes the microscopic, ever-changing structure of spacetime at the smallest scales. Imagine spacetime not as a smooth, continuous fabric, but as an intricate, frothy sea of constant fluctuations, bubbling and rippling due to the influence of quantum effects. In this framework, spacetime at the Planck scale, the unimaginably tiny realm where quantum mechanics governs, is teeming with energy, creating a chaotic dance of tiny, fleeting distortions. These distortions are what scientists call quantum foam. Within this dynamic and turbulent environment, some physicists theorize that it might be possible to exploit the foam's peculiar properties to create shortcuts through time. If spacetime is fundamentally unstable at this scale, could it be manipulated to form pathways, perhaps even portals, that connect different points in time? This idea suggests that by tapping into the chaotic energy of quantum foam, humanity might one day uncover ways to bend or fold spacetime in previously unimaginable ways, bypassing the normal flow of time as we perceive it. However, such speculation is deeply theoretical and faces enormous challenges, both technologically and scientifically. The immense energy requirements and our limited understanding of quantum gravity make this idea firmly speculative for now. Still, the very existence of quantum foam opens up mind-bending possibilities and highlights just how little we truly know about the underlying structure of reality. Could this frothy sea of spacetime fluctuations hold the secret to time travel, hiding in plain sight at the smallest scales of existence? As we ponder this, our journey continues into the more philosophical idea of time travel through consciousness, a concept that shifts the focus from physical manipulation of spacetime to the power of the human mind. Now turning to the intriguing concept of time travel through consciousness, we explore a theory that shifts the focus from complex machinery and physical manipulation of spacetime to the untapped potential of the human mind. Imagine if the key to traversing time doesn't lie in technology but within our own consciousness. Some researchers and philosophers suggest that altered states of consciousness, such as dreams, meditation, or even deep hypnosis, could open doors to past or future events. During dreams, for example, people often report vivid experiences that feel disconnected from the current moment, leading to speculation that the subconscious mind might somehow tap into a different timeline or reality. Similarly, meditation practices have been connected to experiences where individuals feel a profound sense of timelessness or an awareness of something beyond the present. These altered states may act as portals, allowing the mind to bypass the constraints of linear time, even if the body remains anchored in the present. One particularly compelling idea comes from the study of déjà vu, that eerie sensation of having already experienced a current moment. Could this phenomenon be the result of our consciousness briefly aligning with a memory from the future or a parallel timeline? While purely speculative at this stage, such theories raise fascinating questions about the nature of time and the role of human perception in shaping our reality. Even though the scientific community remains skeptical due to the lack of empirical evidence, the idea of time travel through consciousness tantalizes us with its promise of unlocking a hidden dimension of existence in a way that's deeply personal and profound. Could our minds hold the key to bridging the past, present, and future? As we consider this possibility, we now venture into another futuristic concept, the idea that simulated realities might offer a pathway to manipulating time itself. Now turning to the fascinating concept of simulated realities, we dive into a realm where the boundaries of physical laws blur and the rules of existence could be rewritten. Imagine for a moment if our reality were not the base layer of existence but a highly advanced simulation created by a far superior intelligence. This idea, often called the simulation hypothesis, suggests that every experience, every event, and even the passage of time itself could be the result of code running within an unimaginably complex digital framework. If this were true, it opens up the tantalizing possibility that time travel might be achievable not through bending spacetime but by manipulating lines of code. Just as a skilled programmer could rewind, pause, or fast-forward within a video game, a sufficiently advanced entity might be able to alter the timeline of the simulation we exist in. For example, modifying the parameters of the simulation could theoretically allow for revisiting past events or jumping forward to glimpse potential futures. This concept also brings to mind intriguing questions about glitches in the simulation. Anomalies like déjà vu or inexplicable phenomena might hint at errors or deliberate recalibrations within the system. Could those moments where time feels out of sync be the result of adjustments made by a higher intelligence? While this theory remains speculative, it aligns with scientific advancements in artificial intelligence and virtual environments, where researchers are already creating increasingly realistic simulations. If humanity can simulate entire ecosystems or reconstruct historical events digitally, it is not a stretch to wonder whether a far more advanced civilization might have done the same on a universal scale. However, even if we live in such a simulation, the question remains who or what controls the code, and would they allow us access to the controls? As we ponder these profound implications, we turn now to an equally mind-bending idea: Gödel's rotating universe, a mathematical model that suggests a different path to exploring the mysteries of time travel. Now turning to Gödel's rotating universe, we enter a realm where mathematics and imagination intertwine to offer a unique glimpse into the possibilities of time travel. Proposed by Kurt Gödel, a close colleague of Albert Einstein, this model stems from solutions to Einstein's field equations. Gödel suggested a rotating universe, a cosmos spinning on a grand scale, might allow for closed time loops, paths through spacetime that circle back to their starting points. In such a universe, it would theoretically be possible to travel back to a previous moment in time by following a specific trajectory through the rotating spacetime. The elegance of Gödel's model lies in its mathematical precision, offering a thought-provoking framework that challenges conventional understanding of time. However, this theory also faces notable limitations. For one, there is no observational evidence to support the existence of a rotating universe, as most astronomical data suggest that the cosmos is expanding outward rather than spinning. Additionally, the conditions required for such closed time loops to occur would likely conflict with our known physics, raising questions about its practicality in our reality. Despite these challenges, Gödel's work highlights the vast possibilities inherent in Einstein's equations, inviting us to explore unconventional approaches to the mysteries of time. As we unravel the complexities of his rotating universe model, we now shift our focus to another groundbreaking idea: Feynman's quantum time loops, which delve into the quantum realm to redefine our understanding of time travel. Now turning to Feynman's quantum time loops, we delve into an extraordinary perspective on quantum mechanics that challenges our conventional understanding of time. This concept, inspired by the insights of physicist Richard Feynman, suggests that within the quantum realm, particles may not be bound by the linear flow of time as we perceive it. Instead, they could theoretically travel both backward and forward in time, creating loops that defy the everyday rules of cause and effect. Feynman's work revolved around the idea of particles following all possible paths between 2 points, a concept famously represented in his path integral formulation. In this framework, certain trajectories might involve particles moving in reverse through time. Such possibilities, while speculative, offer intriguing glimpses into how time might behave at the smallest scales of existence. It is important to note that this concept remains deeply theoretical, as the quantum world operates under rules vastly different from those governing our macroscopic reality. However, Feynman's quantum time loops raise fascinating questions about the nature of time and causality. suggesting that the fundamental building blocks of the universe might have time travel-like properties. As we contemplate these mind-bending ideas, the boundaries between science and imagination blur, driving us to rethink what we know about time itself. With this exploration into quantum possibilities, we now set our sights on a final speculation, one that looks beyond our planet to consider the notion that advanced civilizations might have already uncovered the secrets of time travel. Now turning to advanced civilizations, we dive into the tantalizing possibility that extraterrestrial beings, far more advanced than humanity, may have already unlocked the secrets of time travel. Imagine civilizations millions or even billions of years ahead of us in technological and scientific understanding. Such beings could possess knowledge and capabilities that seem indistinguishable from magic to us, including the ability to manipulate time itself. Some theorists speculate that what we interpret as UFO sightings or unexplained phenomena might in fact be evidence of time travelers, either extraterrestrial or even future versions of humanity returning to observe or interact with pivotal moments in history. These advanced civilizations might have mastered the laws of physics in ways we are only beginning to theorize, utilizing energy sources and technologies that allow them to traverse not just vast distances in space, but also the fabric of time. Could these visitors be observing us, studying our past, or even influencing events to guide the course of history? This speculation, while unproven, has captivated imaginations and sparked debates in both scientific and philosophical circles. The idea challenges us to think beyond our current understanding of intelligence and progress, urging us to consider a universe where time travel is not merely a theoretical possibility, but a reality that others may already be experiencing. With this thought-provoking notion, we conclude our journey through 25 theories that stretch the boundaries of science, imagination, and the very concept of time itself. With the next phase of the journey in sight, we dive into the profound ethical considerations of time travel. Imagine holding the power to alter the past or shape the future. What responsibilities would come with such extraordinary capability? The potential impact on history is staggering. A single, seemingly minor change could ripple through time, creating unintended consequences that might reshape entire civilizations or erase pivotal events. This raises serious questions about free will. If time travel allows someone to intervene in past events, are they infringing on the free will of those who originally lived through those moments? Furthermore, the potential for misuse cannot be overlooked. From individuals seeking personal gain to governments or organizations wielding time travel as a weapon, the consequences could be catastrophic. Should time travel even be pursued if the risks outweigh the benefits? Would it be ethical to open the door to such technology knowing the harm it could cause? These questions challenge us not only as scientists and innovators, but also as moral beings who must weigh the vast possibilities against the profound responsibility. Time travel, if achievable, could be the ultimate test of humanity's values, integrity, and wisdom. It forces us to consider not just what we can do, but whether we should do it at all. As the next challenge unfolds, we face the staggering technological barriers that stand between humanity and the dream of time travel. First and foremost, energy requirements pose an almost insurmountable obstacle. Theoretical models suggest that bending spacetime, whether through wormholes, warp drives, or other means, would demand energy levels far beyond anything humanity can currently produce or even imagine. To put it into perspective, some estimates propose that the energy needed to create a stable time travel portal might exceed the output of entire stars. Such immense demands raise the question, could we ever harness or even store such colossal amounts of energy safely? Stability is another critical issue. Even if a time machine could be built, keeping it operational without collapsing or causing catastrophic side effects would be a monumental challenge. Theoretical constructs like wormholes, for instance, are predicted to be incredibly unstable, requiring exotic matter with negative energy to keep them open. This type of matter, while theoretically possible, has yet to be observed or created in practical quantities. Without it, any attempt at time travel could result in a collapse of the system, potentially with devastating consequences. Then comes the issue of materials. Constructing a device capable of manipulating spacetime would likely require materials far beyond our current capabilities. Imagine metals or composites strong enough to withstand the immense forces and gravitational effects involved. Such materials might not even exist on Earth or within our current understanding of chemistry and physics. How would we develop or discover them? The synthesis of entirely new materials or the mining of exotic elements from distant parts of the universe could become necessary. Beyond these hurdles, there are likely countless other unknowns, unforeseeable challenges that may only arise once humanity begins to truly experiment with the fabric of time. Each step forward would undoubtedly reveal new layers of complexity to overcome. The path to achieving time travel is not just a test of our technological ingenuity. It is a challenge that will push the boundaries of what humanity can conceive and create. Yet, despite the enormity of these challenges, the allure of time travel continues to inspire scientists and dreamers alike. With such formidable obstacles, one cannot help but wonder if the advancements needed to make time travel possible would ultimately redefine what it means to be human. Moving forward, let us explore how time travel has captured human imagination in the realm of culture and storytelling, leaving an indelible mark on how we perceive this intriguing concept. From the groundbreaking novel The Time Machine by H.G. Wells, which first introduced readers to the idea of traveling through time via a mechanical device, to blockbuster films like Back to the Future, where a DeLorean car becomes a vehicle for rewriting history and shaping destiny, time travel has consistently been a source of wonder and speculation. Such stories, while fictional, often go beyond mere entertainment. They spark curiosity about the possibilities and challenges of bending time, posing questions that resonate deeply with both audiences and scientists. For instance, the movie Interstellar delves into the relativistic effects of time dilation near massive gravitational fields, offering a visual and emotional representation of Einstein's theories. These narratives not only entertain but also serve as a bridge between complex scientific theories and public understanding, making abstract ideas more accessible and relatable. On the flip side, time travel in pop culture often introduces us to the paradoxes and ethical dilemmas that come with altering timelines. Television series like Doctor Who challenge our views on free will and cause and effect, depicting how even the smallest actions in the past could ripple through history with unforeseen consequences. Similarly, The Butterfly Effect explores how altering a single moment can lead to immense and unpredictable changes in the present or future. These portrayals shape how we think about the moral responsibilities and unintended outcomes of tampering with time. They also reflect humanity's fascination with the what-ifs of history. What if a key event were changed or a great disaster averted? While storytellers may not provide scientific answers, they ignite conversations about the implications of time travel in ways that technical papers alone cannot achieve. By blending creativity with theoretical possibilities, these cultural narratives bring the concept of time travel to life, inspiring both dreamers and innovators to envision a reality where such journeys might one day be possible. Now turning to the philosophical implications of time travel, we encounter questions that strike at the very core of human existence. One of the most profound debates revolves around determinism versus free will. If time travel were possible and the past, present, and future were accessible like pages in a book, does that mean our choices are mere illusions? Would our actions be predestined with every decision already written? Or would time travelers have the power to alter the course of events, introducing true agency? This paradox raises unsettling questions about whether we are masters of our own fate or simply following a preordained script. Another fascinating implication lies in the nature of reality itself. If multiple timelines or parallel universes exist, as some theories suggest, then what constitutes the real timeline? Could our reality merely be one thread in an endless web of possibilities? Time travel challenges us to rethink the concept of a singular, linear existence, pushing us to consider whether every choice we make spawns new realities, each as valid as the next. Moreover, the idea of revisiting or altering the past forces us to confront the ethics of time manipulation. If we could change historical events, would it be morally right to do so? For instance, preventing a tragedy like a war or disaster might save countless lives, but at what cost to the timeline we know? Would erasing one set of outcomes simply create unforeseen consequences, perhaps even worse than the original events? These questions compel us to reflect on our responsibility not just to ourselves, but to the continuum of history and existence. As we ponder these possibilities, time travel blurs the boundaries between science and philosophy, leaving us to wonder whether understanding time is not just about physics, but also about grappling with the essence of what it means to exist. As we draw this incredible journey to a close, let us reflect on the 25 theories that could explain time travel. From the bending of spacetime in Einstein's theory of general relativity to the mind-boggling possibilities of quantum entanglement and multiverse theories, each idea unravels a thread of mystery surrounding time itself. These theories don't just reshape our understanding of physics, they challenge the boundaries of philosophy, ethics, and even the nature of existence. They inspire us to ask not just how time travel might work, but what it would mean for humanity if it ever became a reality. Would mastering time allow us to rewrite history, explore the unknown, or perhaps uncover answers to questions we've barely begun to ask? Or would it confront us with paradoxes and dilemmas we are ill-prepared to face? The allure of time travel lies not only in its scientific intrigue, but also in the profound implications it holds for how we perceive reality, choice, and our place in the cosmos. Could time travel ever truly become a reality, or will it remain a tantalizing mystery forever? We'd love to hear your thoughts in the comments below. Which theory fascinated you the most, and what do you think the future holds for our understanding of time? If you enjoyed this exploration, be sure to like the video, share it with fellow space enthusiasts, and subscribe to the channel. Don't forget to hit the notification bell so you never miss out on our next adventure into the mysteries of the universe. Until next time, keep questioning, exploring, and reaching for the stars.